All right, so we're gonna pick off here where we're gonna pick up where we left off at, which was talking about how transformations, because of log properties, certain transformations are interchangeable given the function. And this kind of goes back to us in pre-AP Algebra 2, where we did the same thing with exponentials and logs. Why do I know that? Because I'm currently doing it right now with this group of students. So if you look right here on example number 4, we graphed our log function, our parent function. So the parent function that we graphed is y equals log base 2 of x. Log base 2 of x, remember saying 2 to what power equals this, right? So 2 to the 0 power equals 1. Therefore, when we graph this, we grow 1, 0, because that's the inverse of that. And so we plotted our points. Here are our points. Now, it says to use the product property to show this is a vertical translation. So to start off with, we have log base 2 of 4x. Log base 2 of 4x is what's the transformation, initial transformation? If I have 4x, what kind of transformation is that? What kind of dial on what? It's a horizontal dilation, right? So we have a horizontal dilation, and x's are liars. So it's not by 4, by a factor of 1/4. Because our x's are liars. So it looks like we're actually at 4, but we're actually at dilating by 1/4. Okay, that's our current position that we're in. So what that means is that if I was to take all of my x values and cut them by 4, like divide them by 4, that would be my new home. Does that make sense? So for example, here, I'm currently at 1, 0. Well, what's 1 divided by 4? 1/4. So it would be over here at now 1/4, 0. Does that make sense? Are you with me? Okay, this one is at 2, 1. So currently at 2, 1. So if I'm at 2, 1, 2 divided by 4 would be 1/2. So 1/2 would now be at 1. Okay, 4 is at 2. What's 4 divided by 4? 1. So now we'll be at 1, 2. 8. 8 divided by 4 is 2. So we'll be at 2, 3. So this would be our horizontal translation. I'm going to do my very best to draw this as if I'm a calculator. Okay, that's it as a horizontal dilation. Do you see how this could also be considered a vertical translation after looking at it? Right? So let's say, how does that work mathematically? So how does this work out to be a vertical translation mathematically? Well, when you have log base 2 of 4x, we can expand that. And that expands to become log base 2 of 4 plus log base 2 of x. So when I expand g of x, I now have a vertical translation. I have a vertical translation of log base 2 of 4. And what is log base 2 of 4? Two to what power is 4? It's 2. So this becomes 2 plus log base 2 of x is equivalent to log base 2 of 4x. Depending on which one you have, you're going to describe the transformation differently. Does that make sense? But they're exactly the same. So when I'm the first one, this is a vertical translation up 2, right? But when I'm here, I'm a horizontal dilation by 1/4. And that's because of that expanding and condensing property of log. So in condensed form, I'm a dilation. In expanded form, I become a translation. I know. Math is crazy. I tell you. All right, so let's look at it for ourselves on a graph. I'm going to reset this. So I'm going to put in first our log function. Y equals log shift dash base 2. That's not a 2. That's a z. Of x. So there's the original, right? Now I'm going to put in y equals log shift dash base 2 parenthesis 4x. Is that not what we graphed on our paper? Now notice when we put in our translation, y equals 2 plus log shift log base 2 of x. That's another x. I don't know why. That's not even where 2 is located. And what did it do to my blue graph? It's the same. It just overlapped it. They're coinciding because they're equivalent. Okay? So one is condensed and one is expanded. And depending on what you're given to, you're going to describe the transformation differently. That's the conclusion of our log properties and how they translate over into the transformation of the log function. All right? Make sense? All right.
Decline. This is Cadet First Sergeant.